Okay, so this is going to be our first full Chapter 8 problem. As you can see, they don't give us the initial conditions this time, so it's up to us. However, we will always need to find the VC of 0 and the IL of 0. Those are the two things that we absolutely need to find on every one of these problems to start off with. So, the switch starts out on and then opens up at t equal to 0. So we'll look at t equal to 0 minus to see what happens here. So after a long time, inductors are shorts. We have the switch is currently closed. Capacitors are open. And we need to find IL and VC. Now, since this here is open, there's no current going that direction, so the only current is going to go this way. And we can find that current there by just doing V over the total R. So IL of 0 minus, which is IL of 0 plus, is going to be 12 over 6. Or 2 amps. Now, it is very, very important that we understand that which way the current's going. So the initial current is going down there at 2 amps, because once I open up my circuit, we need to be careful of our orientations of everything. Okay, now with that said, we have our IL. Now we need our VC. Our VC is over this open side here. Now I do know that the right side of this, if I call this ground, that will be 24 volts. And so I need to find the voltage of this other node here. Well, that voltage in the other node is the same as the voltage across the 1 ohm resistor. And by voltage divider, we can do that, and it's going to be 2 volts. Right, so the voltage there would be 12 times the resistance you're at over the sum of the resistors. Gives us a 2 volt resistance there, and a 2 volt, voltage there. And so what that means then is my VC of 0 is the positive side minus the negative side. 24 minus 2 is 22 volts. So I'm going to go ahead and make a note up here that IL of 0 is 2 amps and VC of 0 is 22 volts. We are going to need those when we're solving our problem here. And it's also important to note that the voltage is measured positive on the right and negative on the left, and the current through the inductor is going down. So all of that was before we even create our differential equation. Now we're going to move in the second stage. And I'm going to erase all of this here. And we're going to go to the second stage of solving this circuit. So now we're going to see what happens after the switch changes. And so at any time after 0, we're going to have this inductor here. We're going to have the resistor. This switch opens up, so basically nothing in here is going to matter. We have the capacitor, which is 0.8. And I do want to point out something. I promised you that we'd only do RLC series or RLC parallel. And you might have complained about it because the original problem was not RLC series or RLC parallel. But notice how we didn't write a differential equation for that part. We only are writing the differential equation after the switch happens. And once the switch happens, it is going to be RLC series. Now it is important that I had the positive on the right, negative on the left, and I had the current going down. So if I want to follow passive sign convention, the voltage across the inductor should be in that way. And once we have this, everything will be fine. Now we had our standard equation for RLC series. I double prime plus r over L I prime plus 1 over LCI is 0. And so my r here is 1 over my L is going to make it 4. And then L times C is 0.25 times 0.8. And let's see here. And then if we reciprocal that, we're going to get 5i equal to 0. So then my characteristic equation, s squared plus 4s plus 5 equals 0. Quadratic formula of this. And you're going to get negative 2 plus or minus I. And so that means my solution here is going to be I of t is a1e to the negative 2t cosine t plus a2e to the negative 2t sine of t. Now, we do have a little bit of an issue here. The issue is that what we have for differential equation for I of t, everything's correct for that, but the thing is that's going to let us find the I of t. And by the way, my I of t in this case is going counterclockwise in order to follow past the sign convention everywhere. And the problem is that they did not ask us for I of t, they asked us for VC of t. Well, okay. One thing we know is that if you have I of t through a capacitor, you can find the V of t through the capacitor by using this formula from chapter 6. And so once we have our I of t here, well, guess what? That we could integrate it and do all this other calculations here, and that would work. The problem is you really don't want to do the integral of things like this, right? You may recall doing things like that in calculus, and they are really awful integrals. So I'm going to let you in on a little secret here. This is the engineer's way of doing it. I'm going to tell you that whether you're looking for current or voltage or anything in this circuit, it's going to turn out that it's going to have the same kind of solution. Now, I don't want to call them A1 anymore because you're going to have different constants here. You are going to have the exact same format, though, the same e's, the same cosines and sines. The only difference is you are going to be able to possibly have a plus c. So whether you're asking to find current through something or voltage through something, when you're resolving any of these problems, it's going to turn out that the solution is going to look the exact same as the default one that we learned in the first slide. The only difference is you will have a plus c that you need to solve for. And that c is always going to be the value of it at infinity. Okay, so we can use our little cheating method here. So in this case, if you see what happens at infinity, these are going to open up, this is going to short, and at that point, since this is an open circuit, nothing's happening, no currents there, so you're going to have the full 24 volt drop across the capacitor, and so my VC infinity, my C value is going to be 24. Now we need to find our K1 and our K2. Well, we know that if you plug in 0, it's going to be 22. And if you plug in 0 over here, the sine part goes away, and you're going to be left with K1 plus the C, which is 24. So K1 is negative 2. Then, in order to figure out what the K2 is, you need to take the derivative. So we need to think about what happens if you take the derivative of VC of t. Well, that's exactly going to be 1 over C IC of t by the formulas from chapter 6, which is going to be 1 over 0.8 times, well, they all have the same current, so it's just going to be I of t as well. And so that would then be VC prime of 0 is 1.25 times I of 0. I of 0 we said was 2 amps. So we're going to get 2.5 here. And then we actually can take the derivative. It's going to be a pain, I know. Using the product rule a bunch here. Let's see. Negative 2 k1 e to the negative 2t cosine t plus k1 e to the negative 2t times negative sine t plus negative 2 k2 e to the negative 2t sine t plus k2 e to the negative 2t cosine t, and the c goes away. So then when you plug in 0 here, you're going to get negative 2k1 plus k2, and that's supposed to equal 2.5 right here. We just solve for that. And so k2 then is 2.5 plus 2 times k1. So that's 2.5 minus 4 is going to be a negative 1.5. And so our final answer then is Vc of t. I'll put the constant first here. 24 minus 2 e to the minus 2t cosine t minus 1.5 e to the minus 2t sine t volts. So I want to show you that these chapter 8 problems are really involved. For the exam, the way I usually break it up is I'll put like a part A that says find IL of 0 and VC of 0, and that'd be worth a good amount of points because that's a decent amount of work just for that part. Then we'd say, you know, write the auxiliary equation, solve for the S values. We do that. Then you write out your generic solution, and then you solve for the K. So it's a multi-step process worth a lot of points, and you will get partial credit based on how much you are able to complete. But regardless, as you can see, this is some of the most involved things that we've had to deal with so far. Okay, so we're going to move on and try some more things.